Hey, so this is my first attempt at one of these videos, so hopefully this goes well. So I'm making this video so that we can begin to move towards solving non-homogeneous equations. So remember that those are the types of equations, so written in general form here, where we have coefficients, and then the right-hand side, the key part, is a function of time instead of being zero. So up till now, we've been focusing on the homogeneous case, which would be where that R of t is zero. And this is from your notes from before, and I'm pointing out that we already have a general theory for how to solve non-homogeneous equations. We just need to learn how to do it in a practical way, right? How to actually find the solution. But the technique is we need to find a particular solution. So we find one solution to the non-homogeneous problem so that when we plug that in, we get R of t. And then if we solve the homogeneous problem, which we just spent so much time learning how to do, right, which takes this form here, c1 times y1 up to yn, where n is the order of the equation. So generally we'll have second order equations, so we'll have two solutions to that. Those are our two roots to the quadratic equation. We take our homogeneous solutions and we just add in the one solution to the non-homogeneous. And that gives us the full solution to a non-homogeneous equation. So when we learn a couple of methods for this, the first one's called the method of undetermined coefficients, we'll keep in mind that the first step of this is always going to be solving the homogeneous equations. And then we just have to kind of pull out of our math butt one solution. So no matter how we find it, if we find it, we can add that in, and now we've got a solution to the non-homogeneous problem. So we've actually done one example of this before, and so this is a very important equation, second order, and this part is the homogeneous, and that's just a simple harmonic oscillator, which we know the solution to that is x of t given here. And this term over here is what makes it non-homogeneous. And that's what's called the forcing term. So we're thinking here that this is like a spring, and every once in a while there's a periodic pushing force on it. So that's called a forced oscillator. And so before, we just guessed what that particular solution was going to be, which takes this form here. And we'll see much more about this later on, but it forms resonance. So that means that if you force the oscillator, the forcing frequency is very close to the natural frequency of the spring, then the amplitude will explode. And so that's obviously very important in engineering applications. But the solution strategy here is solve the homogeneous, find one particular solution, and then add the two together to get the full solution.